This idea was inspired by the curling bridge located in London. I remember seeing a video online in 2013 of the curling bridge and just being amazed and mesmerized by the system and the function that it performed. I remember thinking of how simple yet how intricate this design was. This is when I began thinking of how I could recreate this design with a simpler mechanical system and materials found readily available. I proceeded to make a small-scale model made out of foam core, tooth floss, and straws. After seeing that this idea was possible, I proposed it to a good friend of mine, Christian, as a senior design project. When I proposed it in our senior design class, luckily we had 3 more members join our group and decided to push forward. This is when we decided to join the National Timber Bridge Design Competition.
Further development of this project began at the beginning of the school year in 2013. After some serious brainstorming sessions, we decided to make scale models to nail down our mechanical design. We slowly improved each scale model until we nailed down the design for the mechanical function of our bridge. We then proceeded to analyze the structural integrity of our bridge. We began using hand calculations, then moved to programs more specialized to the unique demands of our design, from Excel to SAP 2000 and finally in Riza 3D. After a long process of trial and error, we finally nailed down our design.
Our main goal was to create a unique drawbridge that would excel in functionality, strength, and aesthetics. Though we enjoyed a challenge, things didn't fall into place for us. This project was a composition of challenges. We didn't have a reliable program which we could use to analyze the dynamic motion. Our solution was to analyze it as a static bridge at different times of its rolling up motion to see where the max stresses were located. We had to keep in consideration deflection, feasibility, practicality, innovation, and aesthetics as we made changes to the design. Our second problem was that as our bridge cantilevered, as it curled, the base experienced a huge moment. We needed to prevent it from tipping, and our most satisfying idea was to anchor the base down with concrete piers. The fact that the bridge had to cantilever meant that it needed to be a lightweight design, which led to our third problem. We had to keep a lightweight design that could also support a 20 kilonewton load, as it simply supported. The more logical idea would be to use a truss design above the joints, but that wasn't an option for this design since the truss would be in the way when it curled up. We analyzed different options and came up with the solution of installing tension-resisting rotating plates at the top of the joints. Below the joints, we placed 2 concrete tiebacks butted at the bolt section and connected with a high-strength industrial bolt.
With our design completed and every foreseeable issue resolved, it was time to begin construction. Construction began in January of 2014. At this point, we were luckily able to adopt 9 more students to help expedite construction and to help us in resolving any issues that may come to the forefront. Construction took place in Campbell, California, at my grandmother's house. A major focus of our team was on the treatment of each component in our bridge in order to ensure lasting durability. The wood members of our bridge are treated with a semi-solid oil-based stain, thoroughly coated on all sides of each member to accomplish a complete waterproof barrier. The metal fasteners and plates were treated with a corrosion-resistant spray primer, and the cables used in our bridge are made of galvanized steel to prevent the ferrous material from rusting. Each component of our bridge is thoroughly treated, ensuring a long design life regardless of its exposure.
Prior to our testing for the competition, we pre-stressed our bridge for a total of 48 hours to help minimize deflection. The competition called for a 20 kilonewton load applied at 4 specific points. As specified by the competition rules, we recorded our deflection values in 15-minute increments over the course of 1 hour. Our maximum deflection was 0.51 inches.
With the competition out of the way, it was now time to test the rolling function of our bridge. Our first attempt took us about an hour due to constantly testing the tension in the cables. But our first roll-up was a success, and we eventually lowered the roll-up time to about 15 minutes.
We were very pleased with the overall design and functionality of our timber bridge. We were able to accomplish our design goals while staying within the constraints set by the competition. We foresee future use of our structure in both military and civil practices, helping troops and civilians traverse rugged terrain or access flooded areas. A big leap toward future development, our bridge serves as a prototype for stronger and lighter designs to come.